Okay, so in the previous video, we found the formula for the dot product, the algebraic version of the formula. So here I'm thinking of a vector specifying a point in the xy plane. So vector has coordinates x1, y1. I have a second vector which has coordinates x2, y2. And what I mentioned or tried to explain is that the dot product between the vectors is then the corresponding products of the entries. So first entry with first entry, and then second entry with second entry, and then you just add the result together. So the formula itself is not too deep from here. Sort of very interesting that this formula has this interpretation in terms of the product of the magnitudes times the cosine of the angle. It's not at all clear from this expression, but let me just do some examples. So like the point of this formula is like, say if one vector represents 1, 3, and then the other vector represents -2, 4, then 1, 3 dot -2, 4, the dot product between these two vectors is the same as well, this one times this one, which is 1 times -2, plus this one times this one, which is 3 times 4, and that gives you -2 plus 12, and this is 10. Okay, so this dot product is 10. On the other hand, right, so again, remember this is like U, this is V. On the other hand, we know that U dot V is supposed to be, well, maybe I'll do this in a second, but let me just, let's keep that for, let's put this on hold. Okay, so we know that that product is 10. Now, what happens if you take a vector with its, as I had said in the past, let's say you have a vector which has coordinates x, y, and there's this magic formula of the dot product of a vector with itself, which, remember, is supposed to give you the norm squared, right? But this is just xy dot xy. And if you follow the recipe, right, this gives you x squared plus y squared. So what we found after taking square roots is that the norm of a vector, right, the norm of this vector u, is the square root of x squared plus y squared. Which obviously should ring a bell because it is nothing but Pythagoras theorem, right? So in a way, secretly the formula for the dot product incorporates Pythagoras theorem in a very natural way. And so how can we use this? Well, remember that we had this specific example, which is U dot V. The formula for the dot product is always norm of U times norm of V times cosine of the angle. So maybe from this picture, it's not clear how would you compute the cosine, the angle between them, theta, but we already know that the left hand side is supposed to be 10, right? If you use this formula that I just found, which is just Pythagoras theorem, the norm of U should just be the square root of 1 squared plus 3 squared. The normal v should just be the square root of negative 2 squared plus 4 squared times cosine of the angle. And then you get that tan equals, well, this, sorry, another technical glitch. I was just saying that if you use the formula for the dot product, right, we have u dot v equals the norm of u times the norm of v times the cosine of the angle, right? We found before that this quantity was 10. Now the norm of u with the formula from Pythagoras theorem is just the root of 1 squared plus 3 squared. Norm of v is root of negative 2 squared plus 4 squared. And then you have cosine of theta. Okay? And so that tells you that 10 equals 1 plus 9 is 10. 4 plus 16 is 20, cosine of theta. And so this tells you that 10 equals root of 2 times 10, right? Because that's root of 200 times cosine of theta, which allows you to solve for theta. And you say that cosine of theta equals 10 over root 2 times 10, which is 1 over root 2, or the same as theta equals pi over 4. So what that means is that in the picture from last, that I had to unfortunately erase, if this was u and this was v, then there was an angle. Well, this looks like more of a 90-degree angle, but really this is pi over 4. Maybe I should do it something like this. Okay? And the point of all of this discussion is that then you can use the dot product to compute angles. So can use using the expression cosine of theta equals u dot v over normal u times normal v. And this turns out to be a very convenient way for computing the angle between two vectors. And I'll tell you more about that with some applications that are actually very interesting. Okay? Now, an extension of this idea is for vectors which are not necessarily on the plane. So let me just mention this quickly, and we'll do more examples about this later. But you could also, instead of just working on XY plane, you can work on XYZ space. And so what that means, first of all, is that there are three unit vectors, I, j, and k. I is, as before, 1, 0, but now you have to add a third entry because there's another axis. J is 0, 1, but again you add a third entry because there's another axis, and k is 0, 0, 1. These you may have seen from your physics classes, these univectors. And the point of these univectors is that I dot I is the same as j dot j, is the same as k dot k, which is just 1, and then that I dot j is the same as I dot k, which is the same as j dot k, which is just 0. Okay? And then in particular, if you have two vectors, which you think of them as position vectors here, so maybe you have a vector u, which has coordinates x1, y1, z1, and another vector v, which has coordinates x2, y2, z2, then u dot v is still x1, x2 plus y1, y2 plus z1, z2. Meaning that still for the dot product of two vectors with three entries, you take the corresponding multiplications, you first entry with first entry, second entry with second entry, third entry with third entry, and then you just add up the answers together. And still, this dot product has the interpretation that u dot v continues to be the norm of u times the norm of v times the cosine of the angle. So the first thing to say is that you can still use this formula to solve for the cosine of the angle. So it's exactly the same formula as before. And the other thing to say is that as a particular case of this formula, you can define that the norm of a vector with itself, u dot u, is just let's say x1, y1, c1 dot x1, y1, c1. So you get x1 squared plus y1 squared plus z1 squared. Okay, so this gives you again the formula. Well, let me just drop the subscripts and call this R for position vector. So this gives you the formula for the norm of a position vector in space. And you should think of this formula as a 3D version of Pythagoras theorem. Okay? So what I will do in the next video is just explain to you how you can use the dot product to find these projections or shadows of one vector along another.